Hey everyone, welcome to The Explainer. Today we're diving into a really fascinating biological paradox. We all know iron is absolutely essential for human life, right? It carries oxygen in our blood, it powers our cells, the whole shebang. But what if I told you this life-giving mineral actually has a pretty dark, hidden side? Today we're unpacking the dangerous phenomenon of iron overload and seeing exactly how too much of a good thing can literally and silently break down the body. Seriously, just think about that core problem for a second. What happens when an essential nutrient turns into a systemic toxin? The human body relies heavily, and I mean heavily, on iron. But here's the crazy catch. We have absolutely zero physiological mechanism to eliminate or excrete the excess. None. Zero. We can absorb it all day long, but we can't actively get rid of it. So when the iron coming in outweighs the tiny amounts we naturally shed, this vital nutrient basically turns into a dangerous systemic flood. Okay, let's dive into our clinical journey today. We're going to cover the biological paradox, the two pathways of buildup, the resulting systemic damage, the high-tech assessment tools used to find it, and finally, reversing the tide. All right, starting off with section 1, the biological paradox. Since our bodies lack an off switch for iron, our only control point is at the doorway, the gut. We normally absorb exactly what we need. But when that delicate system breaks down, or when iron totally bypasses the gut, we're in serious trouble. Check out this number, 200 to 250 milligrams. That's how much iron is packed into just one standard 500 milliliter unit of transfused blood. This perfectly illustrates the massive scale of the problem for patients with severe chronic anemias who need regular blood transfusions just to survive. Literally every single transfusion dumps a massive dose of iron directly into their bloodstream. Because they can't excrete it, that transfusional iron accumulates so incredibly fast, tipping the scales from healthy to straight-up hazardous. And that brings us to section 2, the two pathways. Let's look at how these floodgates open. This slide brilliantly illustrates our two main culprits. On the left, you've got the genetic pathway, hereditary hemochromatosis. Here, a genetic mutation, usually the HFE gene C282Y mutation, causes abnormally low levels of a regulatory hormone called Hepcidin. Because of that, the body just continuously hyperabsorbs iron from food over decades. Now contrast that with the right side, transfusional siderosis. This one is acquired. Patients with conditions like beta thalassemia major need repeated life-saving blood transfusions, which inadvertently load their bodies up with excess iron. It's a classic catch-22. So, where does all this excess iron actually go? That brings us to section 3, systemic damage. Well, when the blood's normal transport proteins get completely saturated, the stuff called non-transferrin-bound iron just floods the plasma. It's a highly reactive, toxic form of iron that sneaks in and silently damages parenchyma cells all across the body. And the systemic complications here? They are absolutely severe. As the iron relentlessly builds up, it damages the liver, we're talking fibrosis, cirrhosis, and even an increased risk of hepatocellular carcinoma. It infiltrates the endocrine system, triggering things like diabetes mellitus or hypogonadism. You can even see the damage on the outside. It causes this striking slate-gray skin pigmentation, which is actually a mix of melanin and an iron storage complex called hemochromatosis. But listen, the absolute most critical organ under threat here is the heart. The heart is incredibly sensitive to iron toxicity, and cardiac failure is actually the leading cause of death for these patients. Moving right along to the climax of our clinical journey, section 4, high-tech assessment. Because this cellular rust builds up totally invisibly inside the organs, modern medicine has had to get pretty clever about detecting it. Doctors basically tackle this enemy from two distinct angles. First, they measure the iron stores themselves using blood tests like serum ferritin, which just skyrockets during iron overload, alongside liver biopsies and specialized T2-star MRI scans to quantify the sheer volume of iron. But, volume isn't everything. So they simultaneously assess the actual tissue damage. They use echocardiograms to see if the heart is failing, plus liver function tests and endocrine screening to see exactly what that iron is breaking. Now, what's really fascinating about this slide is the visual evidence of the toxicity. You're looking at a liver biopsy treated with a special dye called pearl stain. Do you see all those dark blue clusters? That blue staining physically reveals the toxic iron trapped right inside the liver's parenchymal cells. It literally gives us a direct, microscopic look at the massive burden the organ is being forced to carry. And here's how that burden translates over to high-tech imaging. These are T2-star MRI scans. The green arrows point to normal organs, but look at the red arrows. Those super dark areas, that indicates severe iron overload in the liver and the heart. The heart MRI is particularly crucial here. If a patient's cardiac T2 star relaxation time drops under 10 milliseconds, that scan is basically sounding a massive alarm, predicting a very high risk of impending heart failure or arrhythmia. It's just an incredible life-saving warning system. So how do we fix this? Let's wrap up our journey with Section 5, Reversing the Tide. Remember those two different pathways we talked about? Well, because the root causes are fundamentally different, the treatments have to be too. For hereditary hemochromatosis, the primary treatment sounds almost medieval. It's venesection, basically regular bloodletting. By taking out a unit of blood, they remove 200 to 250 milligrams of iron, which forces the body to use up its toxic iron stores to make new red blood cells. Pretty clever, right? But for transfusional patients who are already dealing with severe anemia, you obviously can't take their blood. Instead, they rely on chelation therapy using modern chemical drugs. So the crucial point here is how chelation works around the fact that our bodies just can't excrete iron naturally. Iron chelation therapy involves giving patients specialized drugs, things like Deferasirox, Deferiprone, or Deferisamin. These chelating drugs essentially act like microscopic biochemical claw machines. They circulate through the bloodstream, bind super tightly to the excess toxic iron, and then safely escort it right out of the body through the urine or feces. And the results, honestly, they're incredibly hopeful. Check out this quote directly from the clinical text. Life expectancy has improved dramatically since the introduction of iron chelation. Chelation may even reverse liver, endocrine, and cardiac damage. By pairing rigorous MRI monitoring with this dedicated chelation therapy, what used to be a guaranteed fatal overload is now a highly manageable condition. It's a real game changer. It really is amazing how our bodies maintain such a delicate balance, and just how catastrophic it can be when a single element, like iron, is left without a natural exit strategy. It kind of makes you wonder, what other invisible imbalances are hiding inside us, just waiting to be uncovered by modern medicine? Well, thank you so much for joining me on this explainer. I really hope you found